Okay, this is the second last installment for the series. We started out looking at what we need for accurate results, looked at element types, order, accuracy, distortion, and so on. So today we'll spend on meshing strategies for shells and solids. So it's not quite the same as meshing techniques. It's more the idea of how you mesh and what helps making it easier and better to mesh. Okay, so the last section that we'll cover in the future will be on beam modeling and combining shells and solid models and so on. Okay, so the first part of the session is on surface meshing. Okay, so if you think about surface meshing, if we have geometry, it's pretty easy to mesh. It's very seldom that we have an issue. We may in some cases want to mesh certain regions a bit finer and coarser and so on for different reasons. But the actual meshing itself is you select the meshing type, the surface, element size, and you go. Okay, so what we need to do is we need to choose which element type. So whether it's argument's sake try a quad element, whether it's first or second order elements, we need to pick the meshing strategy. If you're familiar with pattern, you might know paver and isomesh. There's some additional types that you get in some other software. So you have to pick that, and you have to pick the element size. That's pretty much it. Then you mesh. Okay. In a shell mesh, though, the most effort we spend is in setting up that mid-surface model. Not always, but usually. So the process is we need to create mid-surfaces. We may need to trim and extend these surfaces until we get a part that's reasonable to start the analysis on. And at that point, we can start the meshing process. Okay, so to create a more efficient mesh, in other words, a mesh where we have less elements, but the same or better accuracy, we need less elements. So for less elements means we need a finer mesh in certain region, a coarser mesh away from stress concentration. So we can also, to improve the mesh quality or the efficiency, we can decrease the mesh density where there's not much of a stress gradient that exists. Okay, now one thing that we have to be careful of is distortion is a problem, but these distorted elements or bad elements, they're usually okay as long as they're in low stress areas and low stress gradient areas. Okay, so a distorted element degrades in accuracy towards a constant stress element. So both where there's a low stress and a low stress gradient, there's not much bending effects taking place, so they're not that much overstiff. So they actually behave reasonably well. They don't cause significant issues. How we control the mesh density changes is by a series of different options, one being mesh seeds. We can also subdivide the surface, which is something we tend to forget about. Okay, so another one is we can also improve the quality by using some of the feature recognition type of meshing techniques, such as washes around holes and so on. We can also subdivide faces to try and improve the quality. So this is similar to the previous comment on that's one way to both change the mesh density, but also force a nice quality mesh in a specific region. So here's a simple example. A test specimen with notches cut out. And in this region, if I apply a tensile load, I expect the maximum stresses to occur in this region. So if I use a mesh seed, in this case, this was arguments like 0.5 millimeter elements, and these are 2 millimeters. So I specify that on both of these curves, and then I mesh. The disadvantage of this method is if I look in these regions, I see pretty ugly elements. In these regions, they're kind of okay, but these elements just behind it is actually not that good. And this is exactly the area we're interested in. So we need to try and move these elements further away. So while this will still be more accurate than meshing everything with 2 millimeter elements, it's still not an ideal mesh. If I try and split the surface, this is one method where I split that section, I cut out a section over there, and I force an edge where I know the maximum stress will be. It doesn't need to be like that. It just makes your life a bit simpler if you already know where the maximum stress is expected. And by doing that, I can specify different meshes on these. I can even, in this case, it's not that clear there, but you can see the mesh density towards the center is higher than towards the ends. So mesh seed with a fine mesh, but going to even finer in that location. If we zoom into that region, the element quality there is reasonable. It's about 2 elements away. So in other words, a third where we start seeing some bad elements there, slightly closer there. But in the immediate vicinity and most of those is actually pretty reasonable. If I move in this direction there, we start seeing some uglier elements. So that's one way to split the surface, but here's another idea. So in this case, the intent is I want to always use an ISO mesh in this region so I can force really nice shaped elements. But if I look at that region, I expect to end up with pretty ugly elements again there, even though in this region, which is important, I may have pretty good elements. Here's a cleaner way to split the surface. So instead of extending that all the way, I split it off like this. And if I look at these surfaces, they're pretty simple isomeasurable surfaces, which means I can get exceptionally nice elements in this region and then transition to slightly worse. So if I mesh this, you can see there's a really great set of elements over there. The region that's got worse elements is moved a bit deeper, but even then it's 2 of them there, but then a lot of really nice elements again. There's some bad ones, and there we start seeing slightly worse ones. If I look at the expected stress pattern, I expect to see some kind of a distribution like that. So those edges will not be loaded by much. So it's not too important to have great elements there. But again, we can try and split this in a different way to try and improve the elements in those regions as well. Okay, so the other thing that I did here in this example was these are again 0.5 millimeter elements and these are slightly larger. So I already transitioned to slightly larger, but about let's say 0.7 millimeters, meaning I have less elements that I would have had, but I still have a pretty decent mesh there. But from there on, I can transition to significantly larger elements. Okay, then examples of feature meshes. If I have a couple of different sized holes in a plate, something we often see, and I just use a plain meshing, I'll see these elements around there. It's not that bad, but over there it's not great. That one is a lot worse with these weird element shapes there. This one actually came out pretty reasonably. If I use a feature type mesh, something like a washer in this case, I can specify these semi-perfect elements surrounding the holes. So in this example, I specified I want 2 elements surrounding it, and I specified the ratio of what those length to the second element's length should be. So you can already see some issues if you're again trying to do everything simultaneously. These elements are squashed a bit in terms of it's short radially and a bit longer in the circumference, while these are the opposite. So ideally, I want to move that row of nodes closer, so that first row of elements is a thinner section. This one actually came out pretty decently, and the growth in element was worked out well as well, where both the first and second row is close to 1 aspect ratio for most of the elements. Then if you go over to solid meshing, when we solid mesh, we have the choice between do you want or do you plan to build a runtime efficient mesh, which means in most cases you'll try and use X elements with appropriate refinement wherever needed. This compared to a TET mesh means we'll have less nodes and elements for the same accuracy, but it usually requires more and in most cases a lot more user input. So some of these models can take a really long time to mesh when you compare it to a TET mesh. A TET mesh, on the other hand, is meshing time efficient. In other words, it's in terms of your time, it takes a lot less time to mesh. The downside is we end up with a lot more nodes and elements. So that can cause issues in terms of how long the model takes, but also how much memory you need on the machine to be able to solve it, which in turn can impact the cost of your solver. So it's a lot less hassle to obtain a mesh, but it can be a lot more hassle to obtain a mesh that your computer can solve if it's not large enough. Okay, so actually I want to quickly go back to this slide. If I look at the the choices between a runtime efficient mesh or a meshing time efficient mesh, it critically depends on what you want to do with the model. Take an example where I've got a structure that's linear and I only plan to do a single analysis on that. If I have 2 million elements and I have to wait even a day, which I know it's not going to take that long, but let's say you wait a day for an answer, but it took you 5 minutes to mesh, while the X mesh, if it's a really complex structure, might take you 2 or 3 days to mesh, but then it runs in an hour. In that case, it doesn't make sense to try and do the X mesh, especially if you realize you need to refine the mesh in a certain region, which is a lot simpler to do with the TET mesh. On the other hand, if you do a nonlinear analysis where it needs, in some cases, hundreds or thousands of iteration, every iteration is a linear static analysis. So where the previous model, arguments I ran for a day, if you now do 10 iterations, it will take 10 days to do. So for a lot of nonlinear analysis, we tend to try and spend a lot more time and effort in getting the runtime down, which means we spend more time meshing. Okay, looking first at TET meshes, again, we need for efficient meshing to have an efficient mesh, so mesh transitions, finer meshes in regions where we're interested in seeing more detailed stresses or expect to see high stresses and stress gradients. So one method is, again, we can seed an edge. So that is something that you're used to doing on a surface. It works vaguely or somewhat on a solid. It doesn't work well on a solid. I'll show an example in a bit. Apologies. With mesh seeding, we have very, very little control of the mesh. We only have control in the regions where there's edges. So it seldom works well. We can also mesh a face, and we treat that as, let's call it a face seed, while the previous one would be an edge seed if such a term existed. So in that case, the solid mesh will match exactly those shell elements for the faces, meaning if you need a fine mesh in a certain region, a certain face, you can mesh that one fine, mesh the solid, and afterwards you delete the shell mesh again. Okay, so we have a lot more control of the mesh in a given region, so any of the surface regions we're interested in. And again, bear in mind, if there's a sub-region that's important, you can split faces again to mesh finer in those regions. You don't need to do the whole model necessarily with a fine mesh. And the last one is, again, similar to surfaces, we can subdivide the solid. Now, once we get to X meshes, it's something we in any case have to do. Whether it's an actual subdivision or a virtual one, which simply means you're kind of splitting a model for the measure to understand sub-regions and so on. It doesn't matter too much. It's still the same process effectively. So in this method, we have a lot of control, and it's pretty nice and easy to combine this with face seeding as well. So here's a simple example. Shaft with a torus kind of a cutout, so a radius cutout. I'm just splitting it in half so that it's easier to see. In this case, I've specified mesh Cs on those locations. If you mesh it from this side, it looks really nice. So it's the finer mesh as expected, and then it transitions to coarser mesh. But if you look at it from the back, you see the issue. Close to the edges, we got really nice fine meshes, but then it transitions to much coarser because that edge seed can only influence the immediate region surrounding it. It cannot directly influence this one. Yes, I know there's methods that you can specify curvature refinement as well. In some cases, it works well. In some models, we have a region like this where we, arguments like, want a fine mesh, but in another region, we're not interested in a fine mesh. And using that, it will force a fine mesh everywhere. If I try face seeding, now in this case, it's simply a surface mesh. So I mesh this with a really nice fine mesh. And then when I mesh the solid, you'll again see this from this side, a much finer mesh. It doesn't even help I show you on that side because it's exactly this mesh that you'll see on the back side. And again, it influences the regions just surrounding it, and then it transitions to coarser elements. So this kind of a model already has pretty decent elements in this region. We do not have much control over what happens towards the inside, especially if you try and go from very fine to very coarse without any intermediate steps. So in this case, you can actually get some weird elements surrounding this region. That gets us to subdividing a solid. So if I take a disk that I cut out there, in this case, I can make that section a lot finer. And the solid on this side, the remaining solid, I can then mesh a lot coarser again. So if I look at that, it's not that clear because that edge you can still see nicely, but the one going up is a bit harder to visualize. But it's exactly from this model that this one was created. So in this case, this whole section was meshed with finer elements. So it doesn't need to be this cutout. It could have been a radius kind of a cutout, whatever kind of a cutout which is easiest to use and easiest to set up, and would result in a reasonable amount of elements would work. Just an example, I took this one to an extreme as well, where I meshed that section extremely fine and then still transition to the same element size that I have on this model. So in this case, I have a lot of control, which if I go back to this slide, I have no control over how far this finer mesh will extend. Okay, then onto hex meshing. The process for hex meshing is drastically different to TET meshing. Even if an automated method exists, it's pretty much always some kind of a combination of different types of extrudes. Linear extrude example, we're meshing this face and it's being extruded down. Yes, the process is automated, so I'm not actually meshing it and extruding it. The software knows that. But what that means is I'm on this face, I can have pretty complex things happening, but in the thickness, the size of the hole may change, and this hole may be at a slight angle, and these edges may not be straight. But in the overall topology of the face on the other side should be simple, and in the thickness direction, not much should happen. So there's an example of a linear extrude, an arc kind of an extrude, so we revolve it around some axis over there. And again, this is actually a nice example of some things that go wrong with solid elements or hexes when we extrude, when we do it surrounding around some edge. We end up with these bad elements on the inside again, where the aspect ratio start getting worse. So in this, ideally, we'll want to split off a section there and mesh this face so that it transitions from a fine mesh to a coarser one, so that you can extrude in that direction. And then finally, there's all kinds of combined and more complex stuff. So this is a solid where similar to these, except the faces are not parallel. Faces may be bent. In this model, it's not, although the sides are bent. So in this case, there's some kind of a slightly more complex extrude, or some people call it a loft from that face to that face. But again, in that direction, nothing much happens. So there's a layer of elements followed by another layer of elements, another layer, but each of those layers has exactly the same number of elements, and the faces has a one-to-one correlation from that face to the face at the bottom. Okay, so if we have a complex part, something a lot more complex than this, we need to break it up into extrudable parts. Now, if we really want to, we can add something like this into this session or this series, but it makes more sense to do separate sessions on nice techniques to break it up. And that's, if you sat in on Paul's session last week, that was pretty much one of the things he was looking at. Okay, now, some of the issues we have with the hex meshes is dealing with mesh transitions. So on the left, I've got a block, and these dotted lines are virtual split lines. So the intent is I want to mesh this fine, and the other side I want to mesh coarse. I can only transition on two faces, but not the third one. The extrude direction, in other words, that direction, if assuming I mesh that face and I move in that direction, I cannot do anything. I can stretch and shrink it in that direction, but I can't change certain element characteristics. Here's an example. If I mesh this face fine and extrude in that direction, I'll have the same number of elements on that face as this one, meaning there's no transition. So in this case, I'll mesh this one with a fine mesh, And there, yes, I could have used the seed to go from fine to coarser, but I want to show something specific. So I used the same edge mesh there as there and there. It's just a coarser one over there. So I go from a fine mesh on this edge to a coarser mesh on that edge, and then it's extruded in that direction. If I zoom into this region, you'll see these really nice elements over there, but as you move in that direction, the aspect ratio starts getting worse. So if I then specified a mesh seed from there to there that says fine and coarser, yes, this element will be closer to square there, but this edge will now still be rectangular, and that one in that direction is also rectangular. So it will still be this squashed kind of an element. Okay, now if I want to refine or unrefine in the vertical direction, in that direction, in other words, I have to do a separate one. So now I mesh this face where I can have fine elements on this side and coarser there, and I extrude it in that direction. And then I keep on swapping these around. So by doing that, I end up, and again on this on purpose, I went from that number of elements on that edge to that number of elements on the vertical edge as well. So that last row of elements is actually the nicely shaped elements. It's the perfect or close to perfect X elements. So then I swap it again. In this case, I went for coarser mesh again in this direction, but I could have done it on top. It's just which direction you're doing it. So the problem with this method keep on being, I can transition it in one, maybe two directions, but I cannot transition it in the third direction. So if I try and do this, what I've done here in just two steps, let's say from there to there and there to there, but to that size, I'll have a massive change in the length of the elements. So I'll have terrible aspect ratio elements there, and I'll get back to pretty decent ones once I get to that side. So you have to do this in several steps. And another issue that is also visible here is, yes, I know there's horrible elements, but I've kept it like that so it's easier to visualize what's happening, where it's fine and coarser. But one of the things you may have to do is use thinner slices for the fine mesh, and as you go coarser and coarser, you may need more and more elements in that direction to be able to transition decently from a coarse mesh to a finer one, or sorry, fine to coarser. Okay. Then, and one of the things that can also go wrong with solids is you get some that's either impossible or extremely difficult to split into bodies, and some is actually not that difficult to split into X-meshable bodies, but you'll end up with terrible element shapes. Here's an example of it's probably possible, and I can think of a couple of ways to X-mesh this, but I know I'll end up with really, really ugly elements in a couple of regions. So this hole is the same part. I've just split it down the center so that you can see on the symmetry plane what it looks like. I've got a hole in this direction, and for this one, ideally, I want to mesh this face and extrude there. But once I get to that center section, since they interfere, there's no way to simply mesh there and then try and continue. If that hole was moved up to this location, then I can split this face, mesh that face in that direction, and mesh this section in that direction. But for something like this, where you have parts or faces that interfere in different directions, it's really hard to X-mesh. Okay, so this means that for X-meshes, there's cases where it will either take a lot of time to mesh, or you can just say, well, it probably makes more sense to TET mesh something. In theory, there are methods that you can combine X and TET meshes with. So you can arguments like have a core of X elements, some very simple shape on the inside, and you glue the TET mesh to it. It's entirely valid and a usable method. It's just something that, again, adds a bit of complexity because you have to check each of those interfaces. But by all means, there will be cases where that's both needed and important to do. Okay, and here's one of the biggest issues. One of the cases where a TET mesh sometimes actually end up with less elements than a X mesh. If I have a block, a simple but very, very chunky solid block, it's really easy to X mesh and TET mesh. But if I want to mesh from a fine mesh on the surface to a coarser mesh on the inside, it's actually pretty hard to do for X elements. This is because I can take this mesh and get it coarser in that direction and this direction, for example. So in other words, fine over there, but then coarser over there and there. But if I want a fine mesh everywhere, I can't transition from there to the other side. So I have to split this block in a very, very weird way, where if I take this face, I move it slightly down and make it smaller. So in other words, is this pyramid kind of shape where you cut off a portion. That kind of a method I can again use to transition, but I'll have to do that multiple times to get to the inside. On the other hand, if I use a TET mesh, I can mesh all the faces fine, and there's two options. I can either say coarsen the mesh towards the inside, so automatically it'll grow the mesh, or alternatively, I can just mesh the part with a large element size, so it will still use the fine elements on the faces, but then use coarser elements towards the inside. Okay, so it's not something that happens a lot, but for really chunky solids, you may actually end up with this kind of an issue. So why would I want a fine mesh on a surface? Well, in a lot of cases, if I have contact, a bearing or something pressing there, I need a fine mesh in that region. But further in, I don't need that. If there's bending on this, again, the inside is not too important. The skin is where the high stresses are and so on. So there are a significant number of cases where the faces of the solid need to be a fine mesh, but you can dramatically increase the mesh size toward the inside. Okay, so that brings us to the end of the session where we spoke about some methods to improve the mesh quality and to get into an efficient mesh for both shells and solids. And as I say in the last session, we'll cover a couple of interesting techniques to model and combine beams and shells and solid models. Thank you for your time.